Hello everyone and welcome back. From the past few sessions, we have been learning about the arithmetic group of instructions. In this session, we are going to learn about the instruction types INX RP and DCX RP. So without any further ado, let's get to learning. Coming to the topics that we are going to cover in this session, at first we are going to learn about the instruction type INX RP. Thereafter, we will learn about the instruction type DCX RP. Let's begin with the first instruction type, that is INX RP. Now coming to the instruction type INX RP, if you notice the mnemonic INX, it stands for Increment Extended Register. So can you tell me, from all the register, which registers are we talking about? Well, you think about it for a moment. Meanwhile, I'll give you some more informations. Execution of the instruction of this particular type will affect none of the flags. Interesting, isn't it? Now let us decode the instruction type INX RP. As I told you earlier, INX, this mnemonic stands for Increment Extended Register. Now coming to RP, what is this? This is the shorter version of register pair. Now the instructions of this particular type fall under the category of 1 byte long instructions. When we are talking about RP, it's pretty evident we are talking about the BC, DE and HL register pairs. And I believe you already got that notion when I mentioned extended register. Let me remind you, when in the mnemonic itself the letter X is included, that stands for the extended register, meaning the latter parts are going to be treated as the extension of the former parts. What I mean by this? The instructions of this particular type are going to be INXB, INXD and INXH. Notice, in all of them, we are only mentioning the registers which are at the former part. In case of INXB, when we are mentioning B, C is being treated as an extension of the register B. Similar to that, for INXD, when D is being mentioned, E becomes the extension of D. And the same can be said for L when we are mentioning H in INXH. L is the extension of the register H. Now let me show you how this type of instructions work using the instruction INXB. Say within the register pair BC, we have got the value F2, 1, 2. Now if the microprocessor executes this instruction INXB, the value within the BC register pair is going to change to F2, 1, 3. Now you might be wondering, we already have an instruction which could perform the same. And that instruction is INRC. So why exactly do we need INXB? Because if you notice, initially the content was F2, 1, 2, and after the execution of INXB, the content became F2, 1, 3. So if we had performed INRC, the contents within the C register, which was previously 1, 2, could have been easily incremented and turned to 1, 3. Isn't it? But no, let me prove that wrong. Say, within the BC register pair, we would like to load an address. And that address is F2FF. Now as soon as we have loaded the value F2FF within the BC register pair, it is not a value anymore, rather it is the address which the microprocessor knows is being pointed by the BC register pair. Now our aim is to go to the next address from this location itself. So let's make use of the instruction INRC this time. Now if the microprocessor executes this, only the contents within the C register will get affected. And incrementing this content, it will turn to 0, 0. I hope you understood why it is turned to 0, 0. Let me remind you, previously we also discussed about it. When we say FF in hexadecimal, incrementing that by 1 will result in 100 of hexadecimals. Now if you think about it, 2 hexadecimal digits are 8 bits in binary, where each of the hexadecimal digits, if represented in binary, will be 4 bits. So according to that, if we talk about 3 hexadecimal digits, that will be 12-bit binary, right? 4-bit in all 3 of them. Now C, being an 8-bit register, can only store 8 bits. And we are talking about 12 bits now. Therefore, the most significant 4 bits or the most significant hexadecimal digit is going to be discarded. And as I mentioned earlier, none of the flags are affected by the execution of neither INXRP, and it was also the same in case of INRC. So excluding the most significant hexadecimal digit, only the remaining 2 digits, which will be 8 bits in binary, is going to be stored within the C register. Now think about it. From F to FF, we were supposed to go to the next location F300. But now look at the content within the BC register pair. It is F200. So basically, instead of going to the next address location, we will end up at a previous location, isn't it? So, for situations like this, we can't use the instruction INRC. On the other hand, if within the BC register pair, we already have the address F2FF, now having this address within the BC register pair will mean that the memory location F2FF is currently being pointed by the BC register pair. Execution of the instruction INXB cumulatively will increment the entire content of the BC register pair. So this address will be converted to F300. And now the microprocessor will know that the memory location F300 is being pointed. So this is the purpose of having the instruction type INXRP. Remember, INX stands for Increment Extended Register, and the instructions of INXRP fall under the 1 byte long instructions category. So that was all about the instruction type INXRP. Let's now learn about the instruction type DCXRP. Now coming to the instruction type DCXRP, the mnemonic DCX stands for Decrement Extended Register. So here also we are talking about the register pairs, and similar to INXRP, execution of this instruction will affect none of the flags. Now the instruction type DCXRP also falls under the category of 1 byte long instructions. It operates on the register pairs BC, DE and HL, and these are the different instructions of this type. These instructions will perform just the opposite of the previous instruction, that is INXRP. Let me show you the working of this using the instruction DCXH. Say within the HL register pair, we have got the value F800. Now can you tell me, if the 8085 microprocessor executes this instruction, what will be the value inside the HL register pair? Notice, it is F800. So what will be the value just before this? It is going to be F7FF. I hope you understood why it became F7FF. Think about it. Previously, the number was F800, and we are talking about one number before that. You can think of that in a different way. To F7FF, if we add 1, what will be the result in that case? Notice, in the least significant 2 digits, we have exhausted the places with the biggest hexadecimal symbol. Incrementing them will reset both of these places, and we will add the next symbol in line, which is 1, to the next symbol or the digit within the 4-digit hexadecimal number. So 7 is supposed to become 8. So the next number of F7FF is F800. But in this particular case, we decremented the content of the register pair HL, which was previously F800, so clearly it will become F7FF, isn't it? So that's all about the instruction type DCXRP. Remember, DCX stands for Decrement Extended Register. For this instruction also, the latter part is considered to be the extension of the former part. And the instructions of the instruction type DCX-RP fall under the 1 byte long instructions category. So in this session, at first we learned about the instruction type INX-RP, and thereafter we learned about the instruction type DCX-RP. The first instruction type increments the contents of the register pair which is mentioned within the instruction, whereas the second instruction decrements the content of the register pair which will also be mentioned within the instruction itself. Alright people, that will be all for this session. In the upcoming sessions, we are going to learn about a couple of more arithmetic instructions. So I hope to see you in the next ones. Thank you all for watching.